All right, we're going to talk about the effects of weight on stability today. And all right. So normally a vessel will be upright and stable in the light ship condition. The manner of which dead weights items are distributed on board is determined by the operator of the vessel. When weights are added, removed or shifted on a vessel, there's a direct effect upon the centre of gravity of the vessel, the stability of the vessel, the draft, the trim, and the centre of flotation of the vessel, and uneven distributions of weight on a vessel will result in a list towards the side which has the greater weight. Whenever weights are added, removed, or shifted on a vessel, the centre of gravity of the vessel will move. The size of the moments or the movement of the centre of gravity is directly dependent upon the size of the weight involved, the distance between the centre of gravity of the vessel and the centre of gravity of the weight being added, removed, or shifted, and the displacement. So it's important in understanding the forces that act on stability. Basically, a long lever is more powerful than a short one. A seesaw or balance bar is a very simple lever. In this animation, the car eventually balances the motorhome on the seesaw, and this happens even though the car is lighter than the motorhome. That's because the car has a longer lever than the motorhome. Oops. The point of balance is reached when the forces generated by the motorhome and the car are equal. The force generated by each result from the length of the lever and the weight, and this is called a moment. The point of balance is reached when the moment of the car equals the moment of the motorhome. If the car continues so that it's even longer lever, its moments will be greater than the motorhome. As the moments depend on both the length of the lever and the weight, the moment of the car could be increased by adding weights to the car, such as passengers. It's important to remember levers and moments when we're adding weights to a vessel. So consider a radar installation. The best radar performance is generally obtained by the largest possible radar scanner, often the heaviest, and the highest possible installation. Sometimes we need a compromise, have to be made, and a lighter scanner fitted, and also sometimes they're lowered in the mast. The movement of the centre of gravity of a vessel can be summarised in 3 rules. When a weight is added to the vessel, the centre of gravity moves towards the weight. When a weight is discharged from the vessel, the centre of gravity moves away from the point where the discharged weight has been located. And the third, when a weight already exists on board is shifted, the centre of gravity moves parallel to the movement of the shifted weight. So our first rule, when a weight's on board, centre of gravity moves towards the weight. So you can see that it was upright and stable in G1. We put a weight on the side, the centre of gravity moved towards the centre of the weight. And we'll list to that side. Same box on the next picture next to that one. We put it down lower in the vessel, not so far off the centre line, so the vessel will list, but it won't list as far as it would have in the first illustration. Of course, it's not as far off the centre line. This one here will list further because that weight is further off the centre line. See, the centre line, the centre of gravity is there. This same weight, if it was the same weight and lower down here, it's not as far off the centre line. The centre of gravity hasn't moved as far off the centre line. It will still list, but won't list as far as what this one would. That would be the same as me on a small fishing vessel or tinny. If I stood right out on the gunnel with my weight as it is, the vessel would list over. If I stood just a little bit off the centre line, it'll still list, but not as far. I'm the same weight, but I'm not as far off the centre line. So it would only list a little bit if I stood here, as opposed if I stood right out here, it would list a long way. You you should be able to picture that in your head. All right, so you can see our centre of gravity here moves up towards the weight when it's added up high, or down towards the weight when it's added down low. So our second rule, when a weight is discharged from the vessel, the centre of gravity moves away from the point where the discharged weight has been located. So the vessel had a weight over here. We were at G1. We took the weight away, centre of gravity moves away from the weight. And now we'll list to this side because the weight's gone here. Same here, the weight, or the centre of gravity is here. We're up nice and upright. We got rid of that weight, centre of gravity moved away. We'll list to this side, but not as far as what we would have listed as opposed to the other weight. And the third one, when a weight already on board is shifted, the centre of gravity moves parallel to the movement of the shifted weight. So it was over on one side of the vessel here, and the centre of gravity was in the centre line. We then moved it straight across the deck onto the other side. Centre of gravity moved out there towards the weight, or with the weight. Same here, it was down at G1 when it was up here. Then we put it down in the build or in the engine bay. Centre of gravity moved parallel to G2. So have a go at activity 4.1. And then there's the answer to it. And 4.2, have a go at that one. The answer to these are in the back of the book. When a weight is added or removed from the vessel, the draft and hence the freeboard will change. And in addition, the centre of gravity will also move to a new position. All right, so we will, if you decrease or increase your freeboard, then your centre of gravity will also change. Deck immersion has a big effect on the shape of the GZ curve. If deck edge immersion occurs at a smaller angle, the whole curve will be reduced from that point onwards, and the maximum GZ will be smaller and the area under the GZ will be lessened. All right, so if you look at these pictures here, got a large deck immersion when it was hanging up, when it goes over, larger angle of heel before that deck edge immersion goes underwater, less freeboard, lower amount of heel for that deck edge to go under. All right, so it's the GZ curve talks all about that deck edge immersion. The angle of deck edge immersion is dependent upon the freeboard of the vessel. If the freeboard is large, the deck edge immersion at larger angles of heel and vice versa. Freeboard is an important factor in determining the vessel's range of stability. So here's a typical GZ curve. So they say that it's all about the deck edge immersion, which is on this GZ curve is here. They say that that's where the deck edge immersion goes under. So the curve comes up, and at deck edge immersion, the curve starts to come down. All right, so that's where sometimes it's hard to see where that deck edge immersion is, but that's the theoretical line of the GZ curve. This here is our maximum GZ. This is our maximum. So this is as long as our GZ is. So our longer that the riding levers are to bring it back. I kind of refer to it as a rubber band. The amount of power it has to bring the boat back to the upright. You can see after that, as we heel over further and further, we have less ability to come back up again. And that kind of makes sense, doesn't it? As you heel over, get to the point where it gets less and less, to the point where we've got no more GZ, which is not a very good day. All right, so a reduction in freeboard is associated with the reduction in stability. An increase in freeboard is associated with an increase in stability. All right, so this one here, the blue line is our standard line. All right, so that's our standard GZ curve. If we reduce our freeboard, all right, so we've got more weight on the boat is deeper in the water. We've got, we're going to get the deck edge immersion being earlier. So the deck edge immersion here with reduced freeboard might be at this point here. So the graph would start to concave down from that point there. If we manage to get a greater freeboard, then that would be deck edge immersion would be later. And you can imagine there that our range of stability is greater, our maximum GZ is bigger because our deck edge immersion is later. And the blue line is just the standard one, what we would normally have. There it is there. So deck edge immersion, from that point onwards, the graph starts to concave down. Now, in vessel design, we try to do a couple of things, don't we? If we have, no, we won't worry about that. We'll talk about that in a minute. So have a go at 4.3 there. All right, so the next one is all about the raising and lowering the centre of gravity. So we've considered the effects of freeboard on stability and the GZ curve. We now need to consider the effects of raising and lowering the centre of gravity also has on the GZ curve. So here it is here. Here we have our standard, our blue again, which is just the normal. And then our red is if we raise the centre of gravity. And this is all about, this starts off right here. Everything is from the 0 mark, as opposed to freeboard. That was talking about deck edge immersion. When we raise and lower the centre of gravity, it affects our stability from the 0 point. So if we raise our centre of gravity goes higher in the boat, we have less stability. A range of stability is less. If we lower it, we put all the weight down low. So we got on board, we're going out for a charter boat. All these passengers came on board with their bags and we put them up high on the boat for some particular reason. The centre of gravity moves up, so we become maybe tender and our range of stability is less. Same passengers, same bags, we put them all down low, way down low in the storeroom, down under the main deck. Our centre of gravity is lowered. We have a better range of stability, greater GZ, and we become stiffer. Our vessel's stiffer, so it will come back up to the upright quicker. This one here, we're tender, so the vessel will roll over and come back up slowly. Now we don't just go throw all our weights down low when we design boats and stick everything right down in the bilge, and we have got a huge GM, so we're really stable, because it becomes very uncomfortable. The boat will come up to the upright really quick and sharp, and movements, and can be quite dangerous. And if we put our centre of gravity too high, we become too tender, we might roll over if we get a bit of wave or wind, and bad stability, all right? So we don't want to be here because it's uncomfortable for everybody. We don't want to be here because it's dangerous, so we tend to take the middle ground. So it's still stable, we can still go to sea, and it's kind of comfortable. That's what we kind of aim for when they're designing stability on vessels. All right, so there's the same one there. So raising the centre of gravity sends our centre of gravity high, putting it weight down low sends it down low. Have a go at that. All right, so using a gear, or gear as in a crane or something like that, that's on the boat. Not a crane that's on the wharf, but a crane or derrick that's on the boat, or high ab, or whatever you want to do. When we talk about lifting a weight with a crane, as soon as we lift the weight off the deck or out of the ocean or whatever, that weight is then transferred to here, to the point of suspension. So that doesn't matter where that weight is. If it's all the way down, that weight all the way here or all at the top, the center of gravity is sitting at that point of suspension. So that's where everything moves forward. So let's now reflect onto this one. You can see the weight's been taken off the bottom of the boat. All right, the grabs picked it up, set and out, and that weight is now suspended here. So the center of gravity moved up to that point there. Now, as we lift the bag up higher, you can see it's still here, the point of suspension. So our center of gravity doesn't move. It doesn't make any difference how high this bag is or the weight, because the center of gravity of that weight is now at that point of suspension. And again here, you can see that the particular weight has moved all the way up, but the center of gravity remains the same. So that's an important thing to think about when you're lifting up a weight on your vessel. So here it is. So we've got our bag, and we might be picking up something from inside the vessel. We picked it up off the deck. Let me just get my little pen. Picked it up off the deck. It had a center of gravity. We picked it up. It moved. That weight moved to the point of suspension. Our center of gravity moved up and parallel to the weight. So it went up to G1, parallel. And then you can see that the crane slewed over. The vessel started to list over because the weight was brought off the center line. And now it's just sitting here at the moment, and our center of gravity moved from here. Of course, the crane was up here and moved down there. Nice straight line. So that's what's that happened there. It's moved across and down. And it's now suspended at that point there. And waiting for the next one. The final one is it's put onto the wharf. The cable goes slack. Center of gravity moved away from that point of suspension to there. It can't go back to the original position because there was a weight here at one stage and we took it off, and now it sits on here. So that center of gravity can't go back to there because that weight is no longer on the boat. So it goes back here. So if you can imagine the second rule, when a weight is discharged, the center of gravity moves away from the weight. So if we just think about that weight there, we took it away, center of gravity moved away from the weight. So that's the final position of G3. Now, the little animation here is a little VW being picked up onto a vessel. So not much happens to the center of gravity, up and across as the crane comes across. Then it's in the center line, lowers down, nothing happens to the center of gravity as it's lowered down into the holding area. Then when the weight comes off the crane, center of gravity moves down. There you go. So have a go at that, that activity. So I'll just read it out then. In the diagram, a load is shifted from the wharf, position 1, and placed in the hold of the vessel at position 2. On the diagram, show by means of arrow the movement of the vessel's center of gravity during this loading operation. Assume that the initial position of the center of gravity is on the center line of the vessel, and show the position of the center of gravity of the vessel when its load is lifted off the wharf, the load is plumbed over position 2, and then the load is finally landed in position 2. So we can say that the first point, we're saying that the center of gravity is there. All right, and then from there, where does that center of gravity go? When it's lifted, when it's plumbed over the top there, where's the center of gravity going? And the final one is when it's actually loaded in the cargo hold. what happens to that centre of gravity. So do that, and in the next picture, so you can probably pause it and do that. In the next picture, it gives you the result. All right, so there's your answer from where it is. You can see that it's gone from the initial one out to the suspension point. You can see it's kind of moved right out there. Then it's slewed up over here. So it's slewed up and it stayed there. It's lowered all the way down, down. It stays here as it's lowered down. Nothing happens. Lowering down, stays here until the point where that wire goes slack. And as soon as it goes slack, centre of gravity moves to its final position. All right, so list and heel. A list is caused by uneven distributions of weights on board the vessel, so that the centre of gravity is not in the centre line of the vessel. A weight is placed on one side of the vessel. As a result, the vessel's centre of gravity will move towards the loaded weight to a new position of G1. Now the force of buoyancy and the force of gravity are no longer acting in the same vertical line, and these two forces will tend to rotate the vessel towards the loaded weight. As the vessel starts to list, the shape of the underwater volume will change and the centre of buoyancy will start moving towards the low side. Once the centre of buoyancy is directly underneath the centre of gravity, the rotation will stop and the vessel will come to rest with a certain angle of list. So here's the deadliest catch and what's happening with ice. All right, so there's deadliest catch and ice and weights, the centre of gravity being raised on that vessel. So a heel, when we talk about a heel is caused by inclination of the vessel under the influence of external forces, such as wind and wave action. We can examine these effects by plotting a heeling or listing lever on the same scale and along the same axis as the riding lever on the GZ curve. All right, so here it is here. Here's our a heel. So we might have an angle of heel, and you can see that it runs down here. So we know that from our previous GZ curve, our GZs, our riding levers were here, our maximum GZ was here, and then as we went over further, less and less until the point where we had no more riding levers. We heel over, let's say we heel to 5 degrees on one side, then we've lost all this stability on that side because we were already heeling over. So our GZs are less now as we go over from there on. So if we've got a constant heel at sea, then we're finding that we've got less ability to return to the upright. Same with the list. If we're listing over, we've got our weights all wrong on the boat, then we've lost all this stability. So it's not a very good thing to go to sea with a list. And if we've got a heel, you know, obviously you get heels all the time, but sometimes you can change course or take some action to reduce that heel. Have a go at that activity. So you may now realise the importance of knowing the vertical height of the centre of gravity. As you load and discharge weights from a vessel, the position of the vessel's centre of gravity changes. A convenient method of determining the position of the centre of gravity is by taking moments about a common reference point. A moment is the product of a weight concerned and the distance it's located from the point of reference. All right, so this is just a load, lots of boxes stacked on top of each other on the ground. All right, now we're trying to find out of these boxes where the centre of gravity is. So metal boxes or metal blocks welded together, the height of the centre of gravity of each individual block above the ground and its weights are shown. We want to find out how high the centre of gravity of the welded blocks is above the ground. And so we're trying to find out the final position of G, which is the total moments divided by the total weights. So their first one is all in kilograms. Block A, or box A. Just move myself over there a bit. Is 200 kilos, and you can see that it's 1 metre off the ground. The next box or block is 1,000 kilos, 2.5 metres off the ground. Next one, 300 kilos, 4 metres off the ground. 600 kilos, 6 metres, and 700 kilos, 7.5 metres. All right, so now we work it out. So our total moments here, 200 kilos times by 1 metre. We get that answer. 1,000 times by 2.5, 300 times by 4, plus 600 times by 6, plus 700 times by 7.5. And then all our weights, our total weights, which is our weights of individual boxes, 200, 1,000, 300, 600, and 700. We do these little calculations. 200 times 100 is 200, plus 1,000 times by 2.5 is 2,500, plus 300 times by 4 is, excuse me, 1,200, and so on. Add these up, our total weights there is 2,800. So our total moments when we do this is 12,750 divided by 2,800. And we get that the centre of gravity of this boxes or blocks welded together is 4.55 metres above the ground. So it's about, centre of gravity is about there. All right, so that's the centre of gravity of those boxes. It is simpler to carry out these calculations in a tabular form. The following table shows the calculations done for the previous example in a tabulated form. And this time we've used weights in tonnes rather than kilos. And that's because we tend to use tonnes in the maritime world as opposed to kilos when we're talking about cargo. All right, so it's the same weights, exactly the same data, just in a little bit different. So, and we talk about weights, and in the next one, VCG. VCG is our vertical centre of gravity, VCG. So item A was 0.2 tonnes, and its vertical centre of gravity of that box was 1 metre above the ground. So weight times VCG is 0.2. B was 1 tonne, 2.5 metres of ground. So weight times VCG, 2.5 tonnes, and so forth and so on. So we get the total of our weights was 2.8 tonnes, and the total moments, when we added up all those moments, was 12.75 tonne moments, and we had 4.55 metres above the ground. So the same way, it's a different way to put it out. Have we got that 4.7 within the tabulated form? So moments are used to calculate the height of the centre of gravity of the vessel above the keel. If you know the heights of all weights on board the vessel, such as fuel and cargo, you can take moments about the keel and find out the height of the centre of gravity of the vessel and its cargo above the keel. The term kg is used to refer to the height of the centre of gravity of the vessel and its cargo above the keel. If the height of the individual weights or items of the cargo within the vessel above the keel. A statement such as there's 50 tonne of cargo in hold kg 3.4 metres means that the centre of gravity of the cargo in that hold is 3.4 metres above the keel. When we find the kg of the vessel after adding and removing some weights, we usually refer to it as the final kg. Therefore, the formula to find the final kg can be written as final kg, final moments divided by final weights. All right. Now, in your FV Tamer book, which is this little one, it has a number of displacement tables and so forth in there. Now, I'll make another video just talking about that book, but I'll quickly just go over this particular slide, and then it's probably prudent to quickly look at that video that I break down that FV Tamer book in conjunction with this particular part of the lecture. But anyhow, we'll go with this one at the moment and I'll explain it as we go. So let us explain the concept of moments by taking a loading condition in the FV Tamar from its stability book. Condition 3, departing the fishing ground. Tank contents, stores, crews and effects, lightships, sullage, sewerage, and each has a weight. Let's consider the longitudinal moments of tanks, conditions and the conditions of loading. Notice how we can visualise them better if we string the weights along a horizontal line in accordance to how far they are from the midships and the name. We name them positive and negative for aft. I'll quickly go to the next slide and come back to this one. When I talk about that, there we have our profile picture for all our weights in that condition 3 on the vessel. So you can see that they're all strung along that line. And in regards to that, you know, here's our forepeak, which has normally got fresh water in it. It's got a kg, so keel to the centre of gravity of that particular forepeak is about 3 metres. All right, so it's 3 metres from there to the keel. It's got a vertical centre of gravity, a longitudinal centre of gravity. How far is it forward of midships? It's about 9 metres. You know, I'm just having a bit of I'm only eye glancing that, but 9 metres. So its longitudinal centre of gravity is 9.0 metres forward because it's forward of midships. The fuel oil number 1 here, it has a kg of about 1 metre. So it's about 1 metre off the keel, probably a little bit higher, 1 point something. And it's about 4.5 metres forward of midships. The fish hold, kg 3.14. So somewhere around here, I'm not quite sure where the centre of the fish hold is, but here. Longitudinal centre of gravity, 2.44, so it's there. So kg, centre of gravity of fish hold is there. Now you can see that our number 2 fuel oil is aft. So the centre of gravity of the fuel oil, number 2, is in the aft part of the vessel. Fuel oil 3 is in the aft. The transom, fresh water, is in the aft. Sorting tray, and so forth. So looking down from a bird's eye view of our fuels and water, fuel oil 1 port, 1 starboard, forepeak, 2 port, 2 starboard. These are identical tanks on either side of the vessel, hold the same amount of fuel. These hold the same amount of fuel, 2 port and 2 starboard, 3 port, 3 starboard, carry the same amount of fuel, and same with the transom tanks, just located on either port and starboard. We'll go back to this other slide. Go back. Bear with me. All right. So you can see on this particular slide that our rows are 1 to 17, and that's just talking about our rows that way. So we can theoretically add more stuff in there if we wanted to, but for this particular exercise, departing the fishing ground, we've got 100% fuel and 100% water. So we're ready to go, fueled up. Our column here, this is all our stuff that we've got on the boat. Our forepeak got water in it. It's got 4.2 tonne in it. We know that a forepeak's got a kg, how high that forepeak is above the ground. And this is weight times kg. And then that particular forepeak has a FSM, our free surface moment, which we talk about later on, but everything that has liquid in it has free surface. It's got a longitudinal centre of gravity for the forepeak. And then our moments, longitudinal moments, go in here, weight times LCG in our forward part, because that forepeak is in the forward. These 2 columns are the same. It's just where those tanks are situated. We know that fuel oil number 1, port and starboard, in the forward part, so the answers go here. Fuel oil 2, port starboard, are in the aft part of the vessel, so their answers go in this column, and so forth and so on. Our dead weight down here is all about this here is dead weight. This is the weight that we put on. This is the light ship before we put everything on here. That's our total displacement. This is our KGF. We spoke about kg so far, keel to the centre of gravity, and F stands for taking into account all our free surface. So when we do this tabulated form, there's our total free surface that we add up to get kgf. And now we explain that further. Longitudinal centre of gravity, where our longitudinal centre of gravity is, and whether it's aft or forward, and in our trim. That's how that particular one's broken down. In the stability book, they've got lots of conditions. And again, refer to my video on the FV stability book to answer those questions. On that one, have a go at that one. Looking at that particular tabulated form, exactly the same as those boxes. It's the same way as the boxes, except now we're just referring to maritime stuff, and we talk about the keel as opposed to the ground. All right, so we're trying, at the end of the day, we're trying to find out what GM is. When they talk about stability, they all talk about GM. What is our centre of gravity to our metacentre? All right, so when we do that tabulated form, we find out what the kg is. All right, so I'll just go back a couple. We know what our kg is. There it is there, or kgf. So we know what kg is, but we need to find out what km is. And so again, the FV Tamar book will give us that information. In the last page, we've already looked at the hydrostatic particulars a couple of times during the other chapters when we talk about TPC, but km is in there as well. So if we know the displacement, and we do, because when we work out kg, we have to know what the displacement is. We can go to the particular hydrostatic particulars, let's say the displacement, and we find out it's 204. We go to the displacement tables in the FV Tamar, and we can find that the last column, it says km 4.55. So km is in the hydrostatic particulars in the FV Tamar book, and it's all to do with what the displacement is of that vessel when you work out kg. So that km changes with displacement. All right, so we know what km is because we go to the hydrostatic particulars. We know what kg is because we've done all the workings to find out. We take those two away, km minus kg will give us our gm. What is our final gm of the boat? And then there's an IMO requirement. All right, have a go at that activity 4.9. And then a progress check. Then we'll move on to the next one after that.